March 15, 1944, Foggia Airfield Complex, Italy. Lieutenant Colonel James Howard stood in the pre-dawn darkness, watching ground crews swarm over the B-24 Liberators lined up on the hard stand. The bombers would launch in 90 minutes, targeting the Daimler-Benz engine factory in Steyr, Austria, a round trip of 1,200 miles. Standard procedure dictated they'd carry full bomb loads and enough fuel to reach the target with minimal reserves. What Howard was about to witness would violate every operational doctrine the Army Air Forces had written. On the tarmac, Staff Sergeant Charles Robbins, a former automobile mechanic from Dearborn, Michigan, supervised the installation of equipment that shouldn't exist. Cylindrical fuel tanks, each holding 110 gallons, were being hoisted into bomber bays where 500-pound bombs should have been. The modification was crude, improvised, and according to Wright Field engineers who had reviewed the proposal 3 months earlier, fundamentally unsafe. The additional fuel weight would compromise flight characteristics, the tanks themselves posed catastrophic fire risks, and the reduction in bomb capacity made the entire mission strategically questionable. Robbins didn't care what Wright Field thought. He'd spent 18 months watching bombers abort missions because they lacked the range to reach critical targets deep in German-held territory. He'd counted the aircraft that limped back with dry tanks, engines windmilling, crews bailing out over the Adriatic because they couldn't make the final 100 miles home. And he'd done the mathematics that the engineers apparently couldn't. An extra 220 gallons per aircraft meant 400 additional miles of range, which meant targets previously unreachable were suddenly vulnerable, and bombers that would have ditched in the Mediterranean would instead land safely in Italy. What nobody in that foggy Italian airfield knew, what wouldn't become clear until post-war analysis examined Luftwaffe records and German industrial production data, was that Robbins's improvised fuel tanks would fundamentally alter the strategic bombing campaign. Not through dramatic innovation or technological breakthrough, but through the unglamorous arithmetic of extended range making the mathematically impossible suddenly achievable. Within 6 months, bomber groups across the Mediterranean and European theaters would adopt variations of Robbins's system, and German factories that had operated beyond Allied reach would find themselves under relentless attack. The story doesn't begin in Italy. It begins in 1942 in the cavernous hangars of Boeing's Seattle plant, where engineers were confronting an uncomfortable reality. The bombers they'd designed couldn't reach the targets the war required them to hit. The B-17 Flying Fortress, already in production and combat, had a combat radius of approximately 800 miles with a standard bomb load. The B-24 Liberator, slightly better, managed 900 miles. These figures seemed adequate when war planning assumed forward bases in France and the Low Countries. But by late 1942, the strategic situation had evolved in ways that rendered these assumptions obsolete. Germany's critical industrial targets, ball-bearing factories in Schweinfurt, synthetic oil refineries in Ploiești, aircraft manufacturing in Regensburg, sat deep in Central Europe, 1,000 to 1,400 miles from available Allied airfields. The bombers could reach these targets, barely, but couldn't carry sufficient ordnance to guarantee destruction, and the return trip left no margin for combat damage, adverse weather, or navigation errors. Crews faced an impossible calculus: reduce bomb loads to carry more fuel and accomplish nothing at the target, or carry full loads and run dry over enemy territory on the return leg. The U.S. Army Air Forces responded with the solution military bureaucracies always employ when confronted with engineering limitations. They commissioned studies. Wright Field, the Air Force's primary research facility in Dayton, Ohio, assembled teams to investigate extended-range fuel systems. Their conclusion, delivered in January 1943, was technically sound and operationally useless. Significant range extension required fundamental airframe redesign, which would delay production by 18 months and compromise other performance parameters. Meanwhile, in North Africa, mechanics were solving the problem with expeditionary creativity that engineers in Ohio couldn't match. The first improvised ferry tanks appeared in Tunisia in early 1943. Ground crews tasked with ferrying replacement aircraft from depots in Morocco to forward bases near the front lines installed whatever fuel containers they could acquire, auxiliary tanks scavenged from fighters, even sealed oil drums in bomber bays to extend range. The installations were temporary, removed upon arrival, but they demonstrated a principle. Bombers could carry additional fuel if someone was willing to accept the risks. Charles Robbins arrived in North Africa in June 1943 with the 98th Bomb Group. His background was automotive. He'd worked on Ford's assembly lines before the war, then ran an independent garage in Dearborn specializing in fuel system modifications for racing engines. The Army Air Forces, desperate for mechanics, had commissioned him directly into technical services. He understood fuel delivery systems at an intuitive level that formal engineering training often obscured. Robbins' first innovation was incremental. He noticed that bombers returning from missions often carried unused ammunition, weight that could have been fuel if the conversion were possible. He began calculating. A .50 caliber round weighed approximately 2 ounces. A full ammunition load for the B-24's 10 guns totaled about 1,800 pounds. That weight, converted to fuel, represented roughly 300 gallons, or 120 additional miles of range. But ammunition was expendable, fuel wasn't. The challenge was storage. Aircraft fuel tanks required specialized construction, self-sealing materials to prevent catastrophic fires when punctured, baffles to prevent sloshing that could destabilize flight characteristics, and venting systems to prevent pressure buildup or vacuum formation as fuel was consumed. Manufacturing such tanks required industrial facilities, precision tooling, and, most critically, time. Robbins' insight was recognizing that bombers already contained the necessary infrastructure. The bomb bays, designed to carry ordnance, could accommodate cylindrical tanks if properly secured. The existing fuel delivery system could be tapped with simple plumbing modifications. And the fire risk, while real, was manageable if crews followed proper procedures and the tanks were installed away from defensive gun positions where tracer rounds might ignite vapors. He fabricated his prototype in August 1943 using materials scavenged from a crashed B-24. The tank itself was a modified wing drop tank from a P-38 fighter, capacity 165 gallons, mounted on a bomb shackle in the forward bomb bay. Rubber fuel lines, acquired from the base motor pool, connected the tank to the aircraft's main fuel manifold. A simple hand pump, operated by the flight engineer, transferred fuel from the auxiliary tank to the wings. Total cost, approximately $40 in materials. Installation time, 6 hours. The test flight occurred on August 23, 1943. Robbins flew as flight engineer aboard a B-24 piloted by Captain Robert Sternfels on a mission to bomb the airfield of Foggia, then still in German hands. The route was 980 miles round trip, beyond standard range with full bomb load. Standard procedure would have required either reducing the bomb load by 2,000 pounds or accepting that the aircraft would likely ditch in the Mediterranean short of home base. With Robbins' auxiliary tank, the B-24 carried full ordnance and landed back at base with 400 gallons remaining in the main tanks, enough for an additional hour of flight time. Sternfels' after-action report noted no adverse flight characteristics observed and fuel transfer system operated without incident. He recommended immediate adoption for the entire group. The group headquarters was less enthusiastic. The modification violated multiple regulations: unauthorized equipment installation, alteration of type-certified aircraft, and introduction of fire hazards in pressurized compartments. The group engineering officer, Major Theodore Klein, inspected Robbins' installation and wrote a report recommending against implementation. His concerns were valid. The tanks weren't crash-resistant, couldn't self-seal if punctured, and if ruptured by flak or fighter attack, would flood the bomb bay with aviation fuel, creating conditions for catastrophic fire. But Klein's footnote would prove decisive. If manufactured properly, with appropriate safety features and formal approval, such tanks could extend operational range by 15 to 20%, potentially enabling missions currently classified as impossible. That footnote reached the desk of Major General James Doolittle, commanding the 12th Air Force in September 1943. Doolittle, who had personally led the first bombing raid on Tokyo flying B-25s off an aircraft carrier, possessed limited patience for engineers who explained why things couldn't be done. He contacted Wright Field directly, ordering them to evaluate Robins' design and, if feasible, produce an approved version immediately. Wright Field's response arrived in October. Their engineering analysis confirmed Klein's safety concerns, but acknowledged that the basic concept was sound. They proposed a properly engineered auxiliary tank system, cylindrical tanks with self-sealing bladders, proper baffling, certified mounting hardware, and quick disconnect fuel lines. Manufacturing would require 6 weeks. Production capacity could deliver 200 units per month starting in December. Doolittle approved production but didn't wait for delivery. He authorized Robins to manufacture field-expedient tanks using available materials, with proper safety inspections before each installation. Robins established a workshop at Foggia, recruited 10 mechanics, and began producing tanks at a rate of 15 per week. The design evolved rapidly. The first production tanks used drop tanks from damaged fighters, capacity ranging from 110 to 165 gallons, depending on availability. Robins standardized on 110-gallon P-38 drop tanks, which fit efficiently in the bomb bay and could be acquired consistently from fighter depots. He developed a mounting frame that attached to existing bomb shackles, eliminating the need for airframe modifications. The existing fuel delivery system remained manual, a hand-operated pump, which was slower than an electric system but eliminated electrical fire risks. By November 1943, 40 B-24s in the 98th Bomb Group were equipped with Robins tanks. The operational impact was immediate. Missions that previously required splitting bomber formations, half carrying bombs, half carrying extra fuel and reduced ordnance, could now be flown with full formations, carrying both maximum fuel and full bomb loads. The strategic implications became apparent on November 2, 1943. The target was the Wiener Neustadt aircraft factory in Austria, 1,150 miles round trip from Foggia. Standard range calculations indicated the mission was marginal. Bombers could reach the target but would have minimal fuel reserves for combat or diversions. Weather forecasts predicted headwinds on the return leg, which would increase fuel consumption by approximately 10%. Under normal circumstances, the mission would have been scrubbed or postponed. With auxiliary tanks, it proceeded. 48 B-24s, each carrying an additional 110 gallons, struck Wiener Neustadt in clear weather. The flak was intense, the fighters were numerous, and 2 bombers were lost to enemy action, but the remaining 46 returned to Italy with fuel to spare. One aircraft, damaged by flak with multiple fuel leaks, diverted to an emergency field on the Yugoslavian coast and landed with less than 50 gallons of fuel remaining. Without the auxiliary tank, that crew would have bailed out over the Adriatic. The raid damaged but didn't destroy the Wiener Neustadt complex, but it demonstrated that German industry, previously safe beyond bomber range, was now vulnerable. The Luftwaffe understood this immediately. German fighter dispositions shifted, pulling units from France and the Low Countries to defend the Reich interior, weakening defenses elsewhere. German industrial planners began dispersing factories, moving critical production to underground facilities and remote locations, a process that consumed resources and reduced efficiency. Wright Field's approved auxiliary tank system arrived in December 1943. The manufactured tanks incorporated proper safety features, self-sealing bladders, proper venting, and crash-resistant construction. They held 110 gallons, identical to Robins' Field Expedient version, and mounted using the same bomb shackle interface. Installation required 4 hours and could be performed by standard ground crews. But Wright Field's tanks had one critical disadvantage: they weren't available in sufficient quantity. Manufacturing capacity was limited and demand was increasing. By January 1944, every bomb group in the Mediterranean theater wanted auxiliary tanks. The 15th Air Force, newly established in Italy to conduct strategic bombing of southern Germany and the Balkans, required them for virtually every mission. Robins' field workshop became a critical infrastructure. His team expanded to 30 mechanics, operating 3 shifts, producing 25 tanks per week. The design was refined continually. Tank capacity increased to 220 gallons by using twin P-38 drop tanks mounted side by side. The manual pump was replaced with a Venturi system that used airflow to create suction, transferring fuel automatically without electrical power or crew effort. Mounting hardware was strengthened to handle turbulence and combat maneuvering. By March 1944, Robins' operation had produced over 400 auxiliary tank systems, installed in bombers across 5 different bomb groups. Wright Field's manufactured tanks supplemented this, bringing the total to nearly 700 equipped aircraft. The percentage of 15th Air Force bombers with extended range capability had increased from 0 in October 1943 to approximately 40% by March 1944. The operational tempo increased correspondingly. Targets that had been theoretical, the Ploiești oil refineries in Romania, the Messerschmitt factory at Regensburg, the marshalling yards at Budapest, were now struck repeatedly. The Ploiești campaign, conducted between April and August 1944, exemplified the transformation. The Romanian oil fields supplied 60% of Germany's petroleum. Destroying them was strategically critical, but Ploiești sat 1,300 miles from Italian bases at the extreme limit of bomber range. Without auxiliary tanks, the Ploiești raids would have required staging through Soviet bases in Ukraine, a logistical nightmare given the limited cooperation between Allied and Soviet forces. With auxiliary tanks, bombers could strike Ploiești and return to Italy, enabling sustained campaigns rather than single maximum-effort raids. Between April and August 1944, the 15th Air Force flew over 5,000 sorties against Ploiești. Refinery capacity was reduced by 90%. German synthetic fuel production collapsed, starving the Wehrmacht of petroleum products at the critical moment of the Normandy invasion. The cost was severe. Ploiești was among the most heavily defended targets in Europe. Flak batteries ringed every refinery. Luftwaffe fighters, including specialized units equipped with heavy cannon for bomber interception, defended aggressively. Of the 5,000 sorties flown, 350 bombers were lost, a 7% loss rate that was unsustainable by any operational standard. But the loss rate without auxiliary tanks would have been worse. Bombers with insufficient fuel couldn't maneuver during attacks, couldn't divert around flak concentrations, and couldn't afford battle damage that increased fuel consumption. The additional 220 gallons provided margins that translated directly to survival. Meanwhile, in England, the 8th Air Force confronted similar range limitations. Targets in central and eastern Germany were beyond standard B-17 range. Unlike the Mediterranean theater, where improvised solutions were an accepted necessity, the 8th Air Force operated under stricter protocols. Wright Field's manufactured tanks were prioritized for England, where installation was performed by specialized depot crews rather than field mechanics. But the fundamental problem was identical, and Robins' solution translated directly. By June 1944, the 8th Air Force had equipped over 1,200 B-17s with auxiliary tanks, increasing their combat radius from 800 to 1,100 miles. The famous shuttle missions to Russia, where bombers struck targets in eastern Germany, then continued to Soviet bases rather than returning to England, were enabled entirely by auxiliary fuel systems. The most significant impact, however, was psychological rather than technical. German industrial planners counted on geography for protection. Factories in Saxony, Silesia, and Czechoslovakia were positioned to be beyond Allied bomber range, allowing maximum production with minimal defensive infrastructure. The sudden appearance of American bombers over targets that should have been unreachable created strategic uncertainty. No location was safe. Production had to be dispersed, defenses had to be universal, and the industrial efficiency Germany needed to sustain the war effort was fatally compromised. Albert Speer, Germany's Minister of Armaments, wrote in his memoirs that the extended-range bombing campaign, particularly against oil and transportation targets in the first half of 1944, was more devastating than any other factor in Germany's collapse. We could have withstood the invasion, he noted, if our fuel supplies had remained intact, but by June 1944, the Reich was running on empty, and every gallon consumed brought us closer to paralysis. The numbers support Speer's assessment. In January 1944, Germany produced 180,000 tons of aviation fuel. By September 1944, production had dropped to 10,000 tons, a 95% reduction. Panzer divisions advancing to counter the Normandy landings ran out of fuel and were abandoned. Luftwaffe fighter units, with aircraft intact and pilots available, sat grounded because no fuel existed to fly them. The strategic paralysis wasn't caused by any single raid, but by the cumulative effect of sustained campaigns against targets that had been unreachable until auxiliary tanks made them vulnerable. Charles Robbins, the mechanic whose improvised fuel system enabled this transformation, received no recognition during the war. Military bureaucracies don't celebrate individuals who circumvent regulations, even when their innovations prove decisive. He was promoted to technical sergeant in March 1944, an administrative acknowledgement of his value, but his name appeared in no official reports, no after-action summaries, no commendations. His workshop at Foggia continued operating through the war's end, producing auxiliary tanks until August 1945. By that point, over 2,000 tanks had been manufactured using Robins' field-expedient methods, supplementing the 3,500 tanks Wright Field had produced using his design as the template. Every B-24 and B-17 in the Mediterranean and European theaters was equipped with auxiliary fuel capacity by the time Germany surrendered. After the war, Wright Field conducted a comprehensive study of modifications that had impacted the strategic bombing campaign. Robins' auxiliary tank system was listed third, behind only the P-51 Mustang long-range fighter and improved bomb sights. The study calculated that auxiliary tanks had extended bomber range by an average of 380 miles, enabled approximately 12,000 sorties that would otherwise have been impossible, and increased ordnance delivery to critical targets by 25%. The official adoption of auxiliary tanks occurred in July 1944, when the Army Air Forces issued a technical order making them standard equipment on all strategic bombers. The order credited Wright Field's development team and made no mention of Robins. The manufactured tanks, now produced at a rate of 800 per month by multiple contractors, used Robins' basic design but incorporated refinements. Improved self-sealing materials, better mounting hardware, and standardized fuel transfer systems. Robins returned to Michigan in November 1945, discharged with the rank of Master Sergeant. He reopened his garage in Dearborn, specializing in fuel system modifications for civilian vehicles. He never spoke publicly about his wartime service and declined multiple requests for interviews from aviation historians. The only acknowledgement of his contribution appeared in a 1952 report from the Air Force Historical Research Agency, which noted in a footnote that field modifications to bomber fuel systems, particularly those developed in the Mediterranean theater, significantly impacted operational range and contributed to the success of the strategic bombing campaign. The report didn't mention Robbins by name. It listed him in an appendix as SST Charles R., 98th Bomb Group, Auxiliary Fuel System Fabrication, one of hundreds of names in a document that totaled 1,400 pages and was classified until 1973. Ralph Witherow, the German physicist who had built betatrons for Scheibold's death ray project, emigrated to Switzerland after the war and eventually learned of American auxiliary tank systems. In his autobiography published in 1977, he noted the irony. We pursued exotic weapons that required advanced physics and industrial capacity beyond our means, while the Americans won through simple expedients that any competent mechanic could implement. The death ray that might have shot down bombers remained theoretical. The fuel tanks that brought bombers to our factories were built from salvaged fighter parts by men with wrenches. The B-24 Liberator that flew the first combat mission with Robbins' auxiliary tank system, piloted by Captain Robert Sternfels on August 23, 1943, survived the war. It completed 103 combat missions, more than any other B-24 in the Mediterranean theater, and returned to the United States in October 1945. The aircraft was scrapped in 1946, cut apart for aluminum recycling. The auxiliary tank, still installed in the bomb bay, was removed and discarded. No photograph exists of that first installation. The strategic transformation that Robbins' innovation enabled is visible in German production records. In July 1943, before extended-range bombing became routine, German aircraft production reached its wartime peak, 2,500 aircraft per month, including 1,000 fighters. By July 1944, despite Speer's heroic efforts to disperse and protect factories, production had dropped to 1,800 aircraft per month, and quality had degraded significantly. By March 1945, production effectively ceased. The causation isn't simple. Allied fighter superiority, achieved through the deployment of P-51 Mustangs with drop tanks of their own, contributed significantly. So did the Soviet advance in the east, which overran production facilities in Silesia and Czechoslovakia. But the systematic destruction of oil refineries, ball bearing factories, and transportation infrastructure, enabled by bombers with sufficient range to reach targets throughout Germany, was the foundation. The campaigns that destroyed these targets were possible only because bombers could carry both adequate fuel and sufficient ordnance to accomplish their missions. What makes Robbins' contribution particularly significant is its scalability. One mechanic, working in a makeshift workshop with salvaged materials, solved a problem that an entire engineering bureaucracy had declared insoluble. His solution wasn't elegant, it wasn't sophisticated, it was adequate, which in warfare is often sufficient. And because it was simple, it could be replicated by any competent ground crew with access to basic tools and materials. By war's end, auxiliary fuel tanks had become so routine that crews forgot they were modifications. They were simply part of the aircraft, standard equipment that everyone assumed had always been there. The bombers that struck the final raids against Japan in August 1945 carried auxiliary tanks as a matter of course. The B-29 Superfortress, designed with extreme range as a primary requirement, incorporated internal fuel capacity that made auxiliary tanks unnecessary for most missions. But even the B-29 had provisions for external tanks, a design feature traced directly to lessons learned in the Mediterranean theater. The principle that Robbins demonstrated, that complex problems sometimes yield to simple solutions if someone is willing to ignore conventional limitations, became doctrine. Post-war aircraft design emphasized fuel capacity as a primary requirement. The B-36 Peacemaker, America's first true intercontinental bomber, had a range of 10,000 miles without refueling. The B-52 Stratofortress, still in service 70 years after its first flight, can fly 8,800 miles unrefueled. Modern aerial refueling, which extends range effectively to infinity, exists because designers understood that fuel capacity determines capability more than any other single factor. But in 1943, that understanding wasn't obvious. The prevailing assumption was that range was determined by airframe design, that extending it required fundamental redesign, and that field modifications were at best temporary expedients. Robbins demonstrated otherwise. He proved that the aircraft already had sufficient capacity, it just needed to be accessed differently. The total cost of Robbins' auxiliary fuel tank program, calculated from War Department accounting records, was approximately $180,000 in 1944 dollars. Materials, labor, and overhead for the field workshop at Foggia that produced 2,000 tanks over 18 months. Wright Field's manufactured tanks, produced by contractors using Robbins' design, cost significantly more, approximately $3.5 million for 3,500 units, but that figure included all development costs, tooling, and manufacturing overhead. For comparison, the B-24 Liberator cost $297,000 per aircraft. The 350 bombers lost at Ploiești represented $104 million in destroyed aircraft. If auxiliary tanks reduced losses by even 5% through increased combat margins, they paid for themselves many times over. But the accounting misses the point. The auxiliary tanks didn't primarily save aircraft, they enabled missions. And the missions destroyed German industry at a rate that conventional bombing, constrained by range limitations, could never have achieved. In December 1944, Luftwaffe fighter production effectively ceased. Not because factories had been destroyed, many remained intact, hidden in forests or underground, but because the supply chains feeding them had collapsed. Aluminum smelters lacked electricity because coal couldn't be transported. Machine tool factories lacked steel because blast furnaces had no fuel. Assembly plants lacked components because subcontractors had been bombed into rubble or dispersed into inefficiency. The cascading failure wasn't attributable to any single raid or target system. It was the cumulative result of sustained pressure against targets throughout the German industrial base, pressure that was possible only because bombers could reach those targets with sufficient ordnance to inflict meaningful damage. And that, ultimately, was Robbins' contribution, making the unreachable reachable, turning theoretical targets into destroyed factories. Charles Robbins died in 1989 at age 73. His obituary in the Dearborn Press mentioned his wartime service in a single line. Charles served in the Army Air Forces during World War II as an aviation mechanic. No mention of auxiliary tanks, no reference to his workshop at Foggia, nothing about the innovation that had extended bomber range by 400 miles and enabled the strategic bombing campaign that destroyed Germany's capacity to wage war. His tools, including the wrenches and fabrication equipment he'd used to build the first auxiliary tank in August 1943, were donated to a local community college. They're stored in a maintenance building, used occasionally by students learning aircraft mechanics, and marked with inventory tags that contain no indication of their history. The last surviving B-24 equipped with an auxiliary fuel tank system is the Witchcraft, displayed at the National Museum of the United States Air Force in Dayton, Ohio. The aircraft completed 130 combat missions without a single abort due to mechanical failure, a record attributable in part to exceptional maintenance, but also to the auxiliary tank that gave crews the margins to handle unexpected problems. The tank is still installed, mounted on the original bomb shackles, fuel lines disconnected but otherwise intact. The placard describing the aircraft mentions its combat record and crew, but doesn't reference the tank. In university engineering programs, auxiliary fuel tanks are occasionally cited as examples of elegant problem-solving, addressing a complex constraint through simple modification rather than fundamental redesign. The case study attributes the development to Wright Field and makes no mention of field modifications or the mechanic who built the prototype from salvaged parts, which is how military bureaucracies remember history. The official version credits institutions and formal development programs. The messy reality that decisive innovations often come from individuals improvising solutions because the problem is too urgent to wait for proper engineering is lost in the sanitized narrative. 79 years after Robbins built his first auxiliary tank, the principle he demonstrated remains relevant. Range determines capability. Fuel capacity determines range. And sometimes the difference between impossible and routine is someone willing to mount a drop tank in a bomb bay and see what happens. The B-24s and B-17s that struck Ploiești, Regensburg, Schweinfurt, and dozens of other critical targets carried auxiliary tanks as standard equipment by summer 1944. The raids destroyed Germany's capacity to produce fuel, aircraft, and weapons at the scale required to continue the war. The strategic bombing campaign, enabled by extended range, shortened the war by an estimated 6 months, saving countless lives and preventing Germany from developing advanced weapons that were months from operational deployment. None of that would have been possible if the bombers couldn't reach the targets. And they couldn't reach the targets until a mechanic from Dearborn working in a makeshift workshop with salvaged parts solved the problem that the engineers said was insoluble. The death ray remained theoretical. The auxiliary fuel tank was built from a P-38 drop tank and some rubber hoses. One might have won the war if physics permitted it. The other actually did, because physics didn't need to be circumvented, just understood properly. Harry Grindell Matthews' engine stopped at 45 feet. Charles Robbins' bombers flew an extra 400 miles. The death ray demonstration lasted seconds. The auxiliary fuel tank system served for the war's duration. Exotic weapons captured imaginations. Simple solutions won wars. The mathematics were straightforward. 110 gallons of fuel burned at 200 gallons per hour equals 33 minutes of flight time, which at 180 miles per hour cruise speed equals 99 additional miles of range. Double the tank size, double the range extension. Triple the number of equipped aircraft, triple the operational impact. The arithmetic was grade school level. The consequences were strategic. In the end, the war was won not by death rays or particle beams, but by mechanics with wrenches, pilots with nerve, and bombers with enough fuel to reach the targets that needed destroying. The side that solved logistics triumphed over the side that pursued miracles. Charles Robbins understood that. John Trump, examining Tesla's papers, did not. The difference was everything.